Hi, good morning. I am Praveen. In this series of videos, we are uncovering some topics from the module VLSI design. In the last video, we discussed about MOS transistors. We saw how semiconductor materials are constructed to form various MOS transistors, and we looked at the construction and working of a NMOS transistor, and finally we saw how NMOS and PMOS transistors can be used as switches in digital circuits. Today's topic is CMOS fabrication, and in today's topic we will have the following sessions. Generally start with introduction to the CMOS logic, then the different fabrication steps of a CMOS inverter, and also the masking layers. In the diagram shown, we can see that A input is applied to both PMOS and NMOS transistor, and PMOS conducts when the input is 0. So when we have A input, VDD is transferred to output, so we will have an inverted value of 1. Similarly, when the input is 1, PMOS turns off and the NMOS conducts ground to the output, so we have logic 0. So this is basically a CMOS inverter, and in this set of slides, we will be discussing about how to fabricate a CMOS inverter. So the general view of a CMOS inverter is shown here. We see that there are many layers and many materials which are integrated together. However, they can be categorized into 5 stages. Initially, a SiO2 protective layer is grown over a p-type substrate. Then we have N plus diffusion for an NMOS transistor, P plus diffusion for a PMOS transistor, polysilicon for the gate, and also metal for connectivity. Moving on, we need to understand the importance of the fabrication process. So, fabrication process gives an idea about the performance, cost, and power. For example, if a transistor in a transistor device, if the number of stages are minimum, or the NMOS and PMOS transistor used in an integrated circuits are minimum, it automatically reduces the die area, and hence the cost is reduced. So such critical factors are observed by understanding the physical fabrication process. So generally the fabrication process consists of a sequence of steps. We need to stack different layers, and this is achieved by using a process called photolithography, which will allow light to decide the area where layers are diffused. So in order to discuss about photolithography, so we can see here that generally PN junction is formed with covering the layer of oxide and removing the oxide in a selected region. So we need to remove oxide layers, so where P and N junctions are required to be formed. And this selective removal of oxide is performed by the photolithography process. And we move on to the next one, that is, as we know that the integrated circuit consists of a sequence of layers which are stacked using several masking steps. So the CMOS fabrication process, initially we take a p-type substrate. So this substrate it serves two purposes. It acts as a mechanical support where different layers can be added, and also it acts as an electrical common point where the ground or it can be grounded, and it can be act as a common potential. So first stage is the selection of a p-type semiconductor. Then we need to form an N-well. So this N-well process consists of different steps. We grow a protective layer of oxide over the entire layer. That is called oxidation process. Then we will pattern the oxide to grow the N-well by using an organic photoresist. Then we will expose the photoresist through the N-well mask and etch away the unwanted regions using hydrofluoric acid. And finally, we remove oxide layers using hydrofluoric acid, while the photoresist is stripped using a mixture of acids called the piranha H. Then the well is formed using the diffusion or ion implantation. So if you say diffusion, it takes place in a heated furnace with dopant gases. If you want to form N-well, so N-well dopant gases are allowed to pass through, are stored inside this furnace and heated. So the various donor ions will be formed to form an N plus. The donor impurity ions will be selectively diffused. So the next option available is ion implantation, where the dopant ions are accelerated and blasted into the surface. Finally, any unwanted regions of oxide are removed using hydrofluoric acid, as we saw the earlier step. So the formation of N-well takes place in a sequence of 7 steps, which can be seen here. Initially, we have a layer of SiO2, which is formed by oxidation using the formula Si plus O2 gives SiO2. Usually, this is taken place in a furnace, and then the second process is organic photoresist, which is formed over this SiO2 layer. This organic photoresist softens when exposed to light, and this particular region is removed for using N-well mask. The photoresist in this region is removed. Then we have the SiO2 layer in this region where the N-well is going to be fabricated. It is etched with hydrofluoric acid. Then we have the photoresist also being removed in the adjacent regions. That is removed by using the process called using a mixture of acid. And then we have the N-well formation, that is usually formed using ion implantation or diffusion. Finally, the SiO2 layer is etched using hydrofluoric acid, leaving the substrate and the N-well. So this is the N-well formation. And moving on, we then form the gates. So in order to construct a gate, we already will be coating 2 layers, that is a thin layer of SiO2 and a polysilicon layer. And if you want to understand about polysilicon, we can refer here. The polysilicon deposition is taking place by this equation, where silane is decomposed at high temperatures. And the next, one of the types of polysilicon is metallurgical grade silicon, which is used in, actually it is used in solar cells. So the potential usage of polysilicon is used for conducting gate materials in semiconductor devices, and it has the potential for large photovoltaic devices. So we have discussed about the polysilicon, and we have a thin oxide layer. Then polysilicon is grown over by the process called chemical vapor deposition. And when we want to look at chemical vapor deposition, so it is a coating process using thermally induced chemical reaction at the surface of a heated substrate with reagents in gaseous form. So we saw what is chemical vapor deposition, and the polysilicon gate is formed by stacking two layers, that is a SiO2 layer and a polysilicon layer. And the patterning is done using a photoresist and polysilicon mask, similar to the N-well formation where N-well mask was used. So we move on to the next step, that is N plus diffusion. Here, for initially, we have now the substrate, N-well and gate. So the layer, a protective layer of SiO2 is grown. Then we have the regions where N plus diffusion needs to be made. So we expose these regions using a diffusion mask. Then the N plus diffusion is actually performed using ion implantation. Although the process is ion implementation, we refer to as N plus diffusion because diffusion was the original term coined. So then later when ion implantation was added, the originality of this process was retained as N plus diffusion. And finally, the polysilicon mask and SiO2 were etched. And this is the formation of an N plus region. Moving on, we will look at P plus diffusion. So P plus diffusion is similar to N plus diffusion. Then we apply a thick field oxide layer, and a contact mask is used to diffuse polysilicon contact pads, not polysilicon. A thick field oxide is used to form contact pads. Then we have a metal layer which is done using metal masking and plasma etching, where metallic layers are formed over the contact pads to act as regions where wires can be connected. So this is the CMOS process, and if we look at the masking layers, we find it resembles the stages we discussed earlier: N plus, N-well, polysilicon, N plus diffusion, P plus diffusion, contact and metal. So this sequence of steps is actually also found in the module called linear integrated circuits, and it is very general topic. But the main concept we derive here is, in summary, the various layers are added, and correspondingly the masks are used synchronously to form the various layers. And finally, by optimizing this process, we can generate ICs with limited die area. So now we have automated tools for this process also. So we have come to the conclusion of today's video, and for slides you can contact the below number or email, and I hope you found this session useful. And in the next session we will consider about the various masking layers, how the layout roles are defined for the various masking layers. Thank you.